In the vast landscape of the cosmos, the laws of physics are our most trusted guides. They describe everything from the graceful dance of galaxies to the frantic jitter of a single atom. These laws are built upon deep, foundational principles, symmetries that define the very fabric of reality. One of the most fundamental is the idea that the laws of nature are the same today as they were yesterday, and as they will be tomorrow. One of the deepest symmetries in physics is that the laws of nature remain the same as time passes. But what if matter itself could defy this? What if an object could exist that is caught in a remarkably stable, rhythmic motion, a clockwork pattern that repeats not in space, but in time, all on its own? This is the story of a discovery that began with an idea so audacious, so contrary to our intuition, that many physicists initially declared it impossible. This is the story of the time crystal. The name itself sounds like it was lifted from the pages of science fiction. It conjures images of impossible jewels that hold moments frozen within them, or devices that might allow us to bend the fourth dimension to our will. The reality, however, is far more subtle, and in many ways, far more profound. It represents a new phase of matter, a way for atoms to organize themselves that was, until very recently, completely unknown to science. The journey to find it would challenge our understanding of equilibrium symmetry and the very definition of what matter can be. It is a story that unfolds at the cutting edge of quantum mechanics, a place where our everyday logic begins to fray. To even begin to grasp what a time crystal is, we must first confront what it is not. It is not a perpetual motion machine, a source of free energy that would violate the most sacred laws of thermodynamics. The universe, it turns out, does not give free lunches. But the discovery of time crystals revealed something almost as strange, that under very specific quantum conditions, matter can enter a state of protected, long-lived oscillation, a rhythm that can persist for extremely long times without settling down. This documentary will take you on a journey from a Nobel laureate's impossible idea, through the rigorous debates that followed, and into the laboratories where scientists finally brought this new form of matter into existence. This quest forces us to ask some of the deepest questions in physics. What is a crystal? What is symmetry? And why is it so important to the universe? And what does it mean to break symmetry not in space, but across the dimension of time itself? Our story begins not with time, but with something much more familiar, an object of beauty and order that we can all hold in our hands. To understand the time crystal, we must first re-examine our understanding of the ordinary crystal, the beautiful, ordered structures that have fascinated humanity for millennia and form the very bedrock of our solid world. Their perfect, repeating patterns are the key to unlocking this new, temporal frontier. Look around you. The chair you are sitting on, the ground beneath your feet, the glass in your window, they all seem inert and unchanging. We call this state of matter solid. For physicists, many of these solids have a special name: crystals. From a tiny grain of salt to a flawless diamond, crystals are the epitome of order in the natural world. They are built from atoms or molecules arranged in a perfectly repeating, three-dimensional pattern. This grid-like structure, known as a crystal lattice, extends in all directions, giving these materials their characteristic strength, flat faces, and sharp angles. This internal architecture is what makes them what they are. This underlying order is more than just beautiful. It is a direct consequence of a deep physical principle known as spontaneous symmetry breaking. Imagine a vast, empty space where the laws of physics are the same everywhere. There is no up, down, left, or right. This space has perfect symmetry. Now imagine atoms begin to cool and condense within it. Chaotic atoms cool and swirl. They will not remain randomly scattered. Instead, to reach their lowest energy state, they will lock into place, forming a neat, orderly lattice. Cinematics snap to place and camera pull back to reveal a vast, repeating crystal lattice. In doing so, they have chosen a specific orientation and position. The perfect symmetry of empty space is broken, and in its place, a structured, ordered crystal is born. This is how matter gains form. This concept of breaking symmetry to create structure is one of the most powerful ideas in modern physics. It explains how water freezes into ice, and how fundamental particles acquire mass. The world we experience, full of complex structures and distinct objects, is a direct result of symmetries being broken. Ordinary crystals are the most tangible example of this. They break the symmetry of space. A crystal looks different if you move a little to the left or right, but if you move by exactly one lattice spacing, it looks the same again. Its structure repeats. For over a century, this was our complete picture of crystalline matter. But in 2012, a startling question was posed by the Nobel laureate Frank Wilczek. If a crystal is a substance that spontaneously breaks the symmetry of space, could a substance exist that spontaneously breaks the symmetry of time? Could matter have a ground state, its lowest possible energy state, that is not static and motionless, but instead repeats a pattern persistently in time? This would be a completely new kind of order, a temporal order. It would be an object whose atoms are locked in a perpetual, synchronized rhythm, ticking like a clock for extremely long times. The very suggestion was a profound challenge to physics, hinting that our catalog of the states of matter was incomplete. The idea proposed by Frank Wilczek in 2012 was both elegant and deeply provocative. He asked his fellow physicists to imagine a system in its absolute ground state, the lowest possible energy it can have. According to the laws of quantum mechanics and thermodynamics, this is a state of perfect stillness. At absolute zero, all thermal motion should cease. A quantum system in its ground state occupies its lowest possible energy and cannot give up any more energy. There is no more energy to be extracted. But Wilczek's thought experiment turned this fundamental concept on its head. He envisioned a system of particles that, even in this lowest energy state, would spontaneously begin to move in a perfectly periodic, repeating pattern, persisting for extremely long times. It would be a clock that ticks without being wound, a pendulum that swings without ever being pushed. This was not just a suggestion of movement, but of a very specific, ordered kind of movement. Wilczek imagined a collection of quantum particles, perhaps arranged in a ring. In their collective ground state, he theorized, they might begin to rotate not because of some external force, but as an inherent property of that state of matter itself. The rotation would be perfectly rhythmic, a persistent, synchronized oscillation that can continue for extremely long times without additional energy input. This theoretical object would be a crystal, but its repeating pattern would not be found by moving through space. Instead, the pattern would reveal itself as time passed. You would see the same configuration appear again and again at perfectly regular intervals. He called it a time crystal. The concept was a direct analogy to a normal, spatial crystal. An ordinary crystal breaks the continuous symmetry of space. It looks the same only if you move by a specific distance, one lattice spacing. Wilczek's time crystal would break the continuous symmetry of time. The laws of physics are constant in time. They have what is called time translation symmetry. But a time crystal would not look the same at every moment. It would only look the same after a specific interval of time had passed, its period of oscillation. It would be matter with a built-in, preferential rhythm, a heartbeat woven into the fabric of its lowest energy state. This was an astonishing claim, as it suggested that motion, the very definition of dynamics, could be an intrinsic property of a static ground state. This idea landed like a bombshell in the world of theoretical physics. It was a beautiful, symmetrical argument that seemed to flow naturally from the principles of quantum mechanics. Yet it also brushed up against one of the most sacrosanct areas of physics, thermodynamics. For centuries, physicists and inventors have been haunted by the dream of perpetual motion, a machine that could run forever without fuel. The laws of thermodynamics were formulated in part to explain precisely why such a machine is impossible. Wilczek's proposal, a system moving endlessly in its ground state, sounded perilously close to this forbidden idea. The scientific community was intrigued but also deeply skeptical. The impossible idea had been spoken, and now it had to face the unforgiving scrutiny of physical law. The immediate reaction from much of the physics community was one of profound disbelief. The idea of a system moving in its ground state seemed to fly in the face of everything we know about energy and entropy. The first law of thermodynamics tells us that energy cannot be created or destroyed. The second law is even more restrictive. It states that the total entropy, or disorder, of an isolated system can only increase over time. An elegant infographic illustrating the second law: a hot, ordered system cooling and reaching equilibrium. This is the law that gives time its arrow. It's why eggs don't unscramble themselves, and why a cup of hot coffee always cools down, its heat dissipating into the surrounding air until it reaches thermal equilibrium. A system in its ground state is the ultimate expression of this equilibrium. It has nowhere lower to go. So, when Wilczek proposed a time crystal, a system persistently oscillating in its lowest energy state, alarm bells began to ring. To many, it sounded like he was describing a perpetual motion machine of the first kind, a machine that could generate motion, and therefore work, from absolutely nothing. If the particles in the time crystal were rotating, they possessed kinetic energy. Where did this energy come from, if the system was already in its ground state? Could you, in principle, attach a tiny paddle to this rotating ring of atoms and extract energy from it? If you could, the system would have to drop to an even lower energy state. But it was already defined as being at the absolute bottom. This was a logical paradox. This apparent conflict with thermodynamics fueled intense debate. Physicists are, by their training, deeply conservative when it comes to the fundamental laws of nature. These laws have been tested with incredible precision for more than a century and have never been found wanting. The idea that a system could spontaneously exhibit motion without dissipating energy felt like a violation of these core principles. It conjured the image of a self-winding clock, a concept that has been the graveyard of countless inventors and charlatans. The burden of proof was therefore immense. For time crystals to be real, they had to somehow exhibit this extraordinary behavior without breaking the ironclad laws of thermodynamics. The skepticism was not just a gut reaction. It was rooted in rigorous mathematical theorems. Physicists quickly began to formulate proofs, known as no-go theorems, to demonstrate why such an object simply could not exist, at least not in the way it was first imagined. These proofs argued that for any system in thermal equilibrium, its properties must be static in time. Any motion, any oscillation must eventually die down as the system settles into its true, motionless ground state. The verdict seemed to be coming in loud and clear. Time crystals were a mathematical curiosity, a beautiful idea that was, unfortunately, forbidden by the fundamental laws of reality. The impossible idea seemed, for a moment, to be truly impossible. Despite the powerful arguments against them, the idea of the time crystal refused to disappear. There was something about the sheer elegance of Wilczek's original proposal that captured the imagination. The concept of temporal order was too compelling to dismiss. It hinted that our understanding of matter and symmetry might be incomplete. While the no-go theorems seemed to close the door, they assumed the system was in thermal equilibrium. Equilibrium is the default state for most systems we encounter. A state of balance, of quiet, of unchanging properties. A rock sitting on the ground is in equilibrium. A glass of water at room temperature is in equilibrium. But what if a system never reaches equilibrium? The universe is filled with phenomena not in perfect balance. Life itself is a prime example. Living organisms are dynamic systems that resist decaying into thermal equilibrium. They are what physicists call non-equilibrium systems. Could time crystals be a property of this more dynamic matter? This question shifted the entire direction of the search. The focus moved away from the ground state toward the wild frontier of non-equilibrium physics. This shift was subtle but revolutionary. It suggested Wilczek's intuition was right, but his original framework was too restrictive. The no-go theorems were correct. No time crystal in a closed equilibrium system. But what if you opened the system up? What if you continuously supplied energy not to power motion, but to keep a special, protected quantum state? One that could oscillate forever without heating up or dissolving into chaos. Physicists explored exotic concepts like many-body localization, Floquet systems, ideas from the edge of quantum theory about collections of particles behaving oddly when periodically nudged. The impossible idea was being reborn. It wouldn't move from absolute rest. Instead, it would respond to an external kick in a unique, protected way. Imagine pushing a child on a swing. Push every swing and they swing with you. But push and a child might swing once for every 2 of your pushes. And they could do that for extremely long times, perfectly synchronized, but at a different rhythm. This was the new vision for the time crystal, a non-equilibrium phase with a robust, subharmonic response. To understand this, we must first solidify what makes an ordinary crystal a crystal. Next, we ask a simple question. What is a crystal? By 2016, the theoretical blueprint for a discrete time crystal was complete. The recipe was clear: interacting quantum particles, many-body localization, a periodic Floquet drive. The stage was set for a race to the laboratory. The challenge was immense, requiring exquisite control over the fragile quantum world. 2 independent teams were poised to take on this challenge. Split screen, trapped ion chain, or NV centers schematic with animated lasers. Christopher Monroe's team, a chain of atoms trapped by lasers. Mikhail Lukin's team, engineered diamond impurities, NV centers. The race was on. In late 2016, both teams published results almost simultaneously. They provided the first concrete experimental evidence for time crystals. They turned a decade of theory into measurable lab reality. These were rigorous experiments searching for 2 smoking gun signatures. Signature 1, subharmonic response. Oscillate at a period different from the drive. Specifically, period doubling. Signature 2, robustness of the oscillation. Persist despite imperfect parameters. Stable against small changes in drive frequency and strength. Lasting many cycles without decaying. Experiments nudged and probed to see if the order would hold or shatter. When the data came in, it was unmistakable. Both teams observed period doubling. They drove their systems with sequences of laser pulses. The systems flipped quantum states back and forth at exactly half the drive frequency. The behavior was incredibly robust. It persisted across wide parameter ranges and long times. Protected from thermalization by many-body localization. For the first time, scientists watched time crystals tick. The idea was brought to life twice, in 2 different physical systems. While the trapped ion experiments were groundbreaking, diamond-based experiments were groundbreaking. They were limited to a small number of qubits, typically around a dozen. A key question remained. Is the time crystal a phenomenon that only exists in these small boutique systems? Or is it a scalable phase of matter that can exist in larger, more complex quantum processors? In 2021, a team of scientists from Google's quantum computing division, Stanford, Princeton, and other universities set out to answer this question using one of the most powerful quantum computers ever built. They used their Sycamore processor, the very same chip that had been used to demonstrate quantum supremacy 2 years earlier. The Sycamore chip is a grid of 53 superconducting qubits. These are not atoms, but tiny engineered electrical circuits cooled to near absolute zero, whose quantum states can be controlled with incredible precision using microwave pulses. This platform offered a unique opportunity to study time crystals on a much larger and more programmable scale. The researchers configured a chain of 20 of these qubits to act as their system. The interactions between the qubits were a natural feature of the chip's design, and they could program the disorder by slightly adjusting the properties of each qubit individually, creating conditions that helped suppress rapid thermalization and stabilize the time crystalline phase. The experiment then proceeded much like its predecessors, but on a grander scale. The team applied a carefully choreographed sequence of microwave pulses to the qubits, serving as the Wilczek drive. They then measured the state of the entire 20-qubit chain to see how it evolved. The results were a stunning confirmation and extension of the earlier work. They observed the characteristic period-doubling response across the entire chain, a collective, coherent oscillation that was the hallmark of a time crystal. The larger system size allowed them to study the phase in unprecedented detail, verifying its stability and measuring the boundaries between the time crystalline phase and the thermal phase where the order dissolved. This experiment was significant not only for confirming the existence of time crystals in a completely different kind of hardware, but also for what it represented. It was one of the first major scientific discoveries made on a general-purpose quantum computer. It showed that these complex machines were not just tools for future calculations, but could already serve as powerful, programmable laboratories for exploring fundamental questions about the nature of quantum matter. They provided a new window into the non-equilibrium world, allowing physicists to create and study exotic phases like time crystals that are nearly impossible to realize or observe in any other way. Now, we explore why this is not perpetual motion, clearly and carefully. The idea of a system in perpetual, rhythmic motion inevitably brings to mind one of the most persistent and forbidden dreams in the history of science: the perpetual motion machine. For centuries, inventors have chased the fantasy of a device that could run forever without fuel, a source of limitless, free energy that would violate the fundamental laws of physics. When the idea of a time crystal emerged, a clockwork ticking indefinitely, it's no surprise those old specters returned. It is crucial to be clear: time crystals are not perpetual motion machines. They do not and cannot provide a free lunch. They do not violate any laws of thermodynamics. The first law says energy cannot be created or destroyed, only transformed. A perpetual motion machine of the first kind would violate that by producing more energy than it consumes. A time crystal does not do this. The persistent oscillation of a discrete time crystal is not happening in a vacuum. It responds to an external energy source, the Wilczek drive. Energy is constantly pumped in via laser pulses, microwaves. The time crystal isn't creating motion from nothing. It's part of a driven dynamic process. Time crystals also do not violate the second law of thermodynamics. That law requires total entropy of an isolated system to increase or stay the same. It's why heat flows hot to cold and systems approach thermal equilibrium. A time crystal seems to defy this by keeping an ordered motion indefinitely, but this only works because it's not isolated. It's an open system interacting with the drive. The law applies to the entire setup: the qubits, the driving laser, the surrounding universe. Order inside the time crystal is preserved at the cost of increased disorder elsewhere. The dream of perpetual motion is getting something for nothing. Time crystals do not deliver. You can't hook a tiny generator to a time crystal and extract work forever. Trying would disrupt the delicate quantum state. The interaction would break the many-body localization that protects it, allowing the system to absorb drive energy and heat up. The time crystal in order would melt, and the oscillation would stop. The system isn't a power source. It's a new phase of matter with a protected response to supplied power. Our journey has taken us from a simple, elegant question to the frontiers of modern physics. We began with the familiar order of a spatial crystal, matter that breaks the symmetry of space. We followed a trail of scientific inquiry that led to an entirely new kind of order, matter that breaks the symmetry of time. The time crystal story illustrates how science progresses. It began with a bold theoretical idea from Frank Wilczek, one so counterintuitive it was initially rejected as impossible. It seemed to flirt with perpetual motion, a clockwork that could seem to tick for extremely long times in its lowest energy state, seemingly violating the laws of thermodynamics. But science is rigorous and self-correcting. Intense debate and powerful no-go theorems followed. Physicists concluded an equilibrium time crystal could not exist. That impossibility became a crucial refinement. Researchers looked beyond quiet equilibrium into dynamic non-equilibrium systems. There, driven by an external force and protected by many body localization, the true time crystal was found, a robust new phase of matter. Discrete time crystals were created, first in trapped ion chains, and later on, sophisticated quantum processors. This marks a pivotal moment in physics. It shows our catalog of phases was incomplete. For centuries, we classified matter by static structure: solid, liquid, gas, plasma. Time crystals show matter can be classified by temporal, dynamic properties. They are not a violation of physical law, but an expansion of it. They do not generate free energy, but reveal a stable way quantum matter can organize when held between an external drive and internal quantum mechanics. This discovery opens a new chapter in exploring the universe. It pushes us to ask what other non-equilibrium phases await. Can we create other forms of temporal order? What practical uses might they have? Ultra-precise timekeeping, robust quantum information processing. These questions drive the next wave of research. The time crystal story reminds us that fundamental laws can still surprise. The laws don't change. Our understanding of what they permit continues to grow.